Welcome to RSET Online. I am Krishna Kumar KP. Today I'll be covering a topic called Multiphase Flow in Tubing from Module 4 SATA Petroleum Engineering. Now my contents are organized as introduction, definition, flow regimes, cavitation and erosion, design points in pipeline, and finally reference. Now, as an introduction, we'll go back to the petroleum reservoir formations, which will be containing one layer of impermeable rock, below which there is porous rocky layer, and below that contains the gas plus petroleum formation. Okay. Now the impermeable layer is very important because if that layer is not present there, you could see the gas as well as the light crude will be escaping from the formation. Okay. Now initially the formation contains will be pressurized. It contains a pressure, so that mining will be easier, but as mining progresses it will lose the pressure, so we need to place an injection well here. So upon the pressure drop that is happening here, we inject water into the porous rocky medium, so that water will drive away the gas and oil from the porous medium, so that it can be mined. And okay. Now most formation contains the combination of petroleum and gas along with water and sand. It is common that most well produce this combination of gas and oil, and so multiphase flow is common in all oil wells. Okay. Now definitions. Multiphase flow refers to the fluid flow through pipes in different phases or states. So you can imagine that in water, if you bubble through water in a bucket, that refers to biphase flow. As an example, I can tell you. And usually multiphase flow cannot be eliminated in petroleum mining operation. As you could see here in the diagram, the gas plus oil formation is occurring naturally. It always occurs in the combination only. So when you start mining, the bubbles as well as the lightweight crude will be rushing through the pipes towards the well heads. Okay. Now we will look into the flow regimes of multiphase flow. Shown is an example of vertical multiphase flow. I have only considered 3 cases, actually more than 5 cases on there. The first one is bubble flow, where the most part is liquid and bubbles of gases will be flowing along with the liquid. And in slug formation, larger bubbles will be created because there is, as you can see, the x-axis, the amount of gas rate is increasing through the x-axis. So in slug formation, when you have more gas content, that leads to the regime called slug. And finally annular mist, in which the red dots shown in this figure is actually the liquid droplets. So that liquid droplets will be rushing through the gas flows. Okay, so this has more gas content and this has more liquid content. Now different flow regimes corresponds to a total oil and gas contents of the mining operation. A particular flow regime is determined by the relative amounts of petroleum and gas along with water and sand. So by looking into the flow regime, one can take into account whether what we are mining more, whether it is gas or petroleum. Okay, now I will go to the next section called cavitation. Cavitation is defined as the formation of vapor bubbles of a liquid when liquid flows through the reduced pressure zone in pipelines. Okay, so cavitation creates liquid bubbles, and cavitation can cause surface erosion in pump blades, valve plugs, and even propeller blades. We will see more details as follows. You can see liquid, the green lines are the liquid flowing through the pipelines. Not necessarily it can be a streamlined flow, it can be a turbulent flow also. So when the liquid reaches a restriction, there will be a pressure drop across this region. And when pressure in the downstream is low, when it falls below the vapor pressure of the liquids, naturally the bubbles will be created. So this region represents the portion where the bubbles are created. And gradually, when liquid reaches far downstream, there will be a pressure recovery will be there. At that time, bubbles will be collapsing. It is marked as the stars in this figure. Okay. So whenever this bubbles collapse, that creates shock waves. That shock waves can damage the weaker section in the pipelines. This process is gradual. It's not a sudden process, but it is a gradual process where if this is subjected to cavitation for a longer time, it will erode. And it is depicted in the graph where P subscript P stands for the pressure of the pipeline, and PV stands for the pressure of the vapor pressure of the liquid. So when the vapor pressure, when the pressure of the pipeline falls below the vapor pressure, you can see this red region as the region where the bubbles forms, and when pressure recovers around this region in, with respect to distance, you can see the bubble collapses. Okay. Now I'll show you some figures where the cavitation creates the damage. Okay. The noise due to shock wave produced as a result of implosion of vapor bubbles, the vibration resulting from cavitation will gradually erode the surface of the pipes and associated parts of the machines. A figure below, taken from reference 1, shows the damage caused by cavitation. Okay, you can see the pump's impeller got eroded away due to the cavitation problems. So whatever fluid machinery is associated, that including pipe, control valves, pumps, impellers, propellers, ships propellers, everything, if not properly designed or managed, will the cavitation will create damage. Okay, now we will see a brief analysis on the formation of bubbles and how to minimize the effects of cavitation. So this, you can imagine a bubble which is formed as a process of cavitation, where the pressure exerted internally is the vapor pressure plus the pressure of the gas. Okay, as I told you, the flow regime will be bubble to flow. So gas, along with the gas bubble, some liquid portion will be vaporized to form a bigger bubble. You can imagine like that. So the pressure of the bubble will have two components. One is vapor pressure of the liquid, and the other one is the pressure of the gas. Okay, imagine the bubble is having a radius of r, and what pressure is exerted from outside is the pressure of the pipeline plus the surface tension. I have not gone for any dimensional analysis in this part. Of course, the dimension analysis should be correct, but we have to simplify the analysis, so I have taken only the static equilibrium part, where pressure of the pipe plus 2 times the gamma, the surface tension factor, by capital R, radius, is equal to vapor pressure plus K times K divided by R cubed. Okay, here the PV is due to two components, that is pressure of gas plus vapor pressure of the liquid. So now in the next page we can make a plot of the pipeline pressure and R as given below. So as long as the pipeline pressure is above certain threshold and radius is small, the bubbles will be stable. And when radius is large, the bubbles naturally will be unstable. And also when the pipeline pressure falls below the vapor pressure, it will be only stable for a smaller radius, and above certain threshold of radius, you can see it will become unstable and will start collapsing. So these collapsing bubbles are more worse to the machines, that will create shock waves. Okay, and now design points. Okay, as long as the pipe pressure P subscripted P remains throughout the run above certain thresholds, we can minimize the bubble formation as well as the bubble collapse. explosion or implosion, to be said in layman's terms. This collapse is minimized. You can almost eliminate the effects of the shock waves, right, or the shock waves created by the bubble collapse. Now, apart from point A, modern designs are aimed at anti-cavitation trends. You can make the structure, you can change the geometry of the structure such that the bubble formation is minimal. This can be achieved by some computational fluid dynamics, solving certain computational fluid dynamics problems, or usually in industrial practice they go for empirical designs. Usually the solution of this bubble formation is a Navier-Stokes partial differential equation, mathematically speaking. So generally we don't go for such kind of analysis because the closed form solution is very difficult. We go for a numerical solution, or more better we go for computational fluid dynamics problems. Computational fluid dynamics simulations, and we can come up with good geometric designs so that this problem can be very much minimized. Okay, so coming to an end, conclusion, I am showing this reference, very good PDF file, free to download from web.mit.edu, HML NCF MF 16 CAV PDF. Okay, see you next time. Thank you.